Ah, good. Good. Now we're recording, by God. All right, now. So the game is again, you have this, we're assuming same inflow, same outflow. There's 100 kilograms of salt initially in this tank. Okay. What happens over time as you're running water into this thing? Well, obviously, eventually it's going to be, there's not going to be any salt to speak of anymore. But we know that's kind of a lie too, because we know that there'll always be a trace of salt in there, even if we can't figure it out. So we know it's going to look something like this over time. Okay. We know that the initial amount of salt in the tank, pardon me, is 100 kilograms. Okay. And we know that obviously will change over time. And so we know the thing's going to tend to zero as time goes on. Okay. So we know those things going in. We got pure water here, which means no salt in it. And so here we go. Okay. So those are kind of our assumptions. So what we're trying to do is we're going to get a function that's like x of t is equal to whatever. And the x of t is the amount of salt at time t. Okay. So it's going to look something like this. dx dt, oops, dx dx. dx dx is 1j. dx dt is equal to negative, because it's going out, x over 1,000. Now think about that for a second. Right now we have x liters of, or there will always be x pounds of salt per 1,000 liters. That will always be true. Okay. And then it's going out at a rate. Now remember, this is in pounds per gallon, or I'm sorry, pounds per liter rather in this case. Well, I don't want pounds per liter. I need pounds per minute or second or hour or something time respect wise. Okay. And so if you look at the problem, it says we're pumping in and out at 5 liters, not per minute, per second, 5 liters per second. And it's going out, so it's going to be 5. I'm going to write it as this, liters per second. If you want to put the negative over here and not here, it makes no difference to me. But what is going to end up happening is that the liters cancel out. And what you get is that dx dt is equal to negative 5x over 1,000. Or if you prefer, negative x over 200. Okay. Once you're here, then this, for the first tank, man, you are home free. Let's do this problem. So get dx dt. It's separable, so I'm going to divide both sides by x. Multiply both sides by dt. I'm going to integrate both sides. So the ln of x is going to equal negative 1 or negative t over 200 plus a constant. And then I'm going to exponentiate both sides. And I think I've done enough for this part, so I can kind of speed the process up a little. I'm going to get x equals c e to the negative t over 200. Okay. And then how much was in there initially? Well, if you recall that x of 0 was 100 pounds of salt. If you plug 100 in here for this, then e to the 0 is 1. That kind of means that c there has to then be 100. Okay, and so that's for our first tank. Okay, do you follow the logic on that, guy?
Yeah, that makes sense.
Okay, so then the question is, when will we have only 10 kilograms left? I don't know. So you could do it 100 ways. You could solve it. I personally, this is the 21st century. I don't do a lot of solving if I don't have to anymore. And I think you're silly to spend an hour like doing logarithms just for a good time. Oh, ooh, isn't this sexy? They changed that for us, didn't they? Sorry, I'm just geeked out there for a second. Cool. So 100 e to the, I'll do negative x divided by 100. And I'll just put y equals 10 here, because that's what I'm really interested in. When does it hit 10? And if you zoom out,
Jay, it should be x over 200.
Oh, thank you. Thank you.
You're
Which means it's
welcome.
going to decay slower. And so out here at 460 seconds, which is just shy of 8 minutes, we'll be down to 10 kilograms of salt in this thing. Okay. So there's that. That's cool. But what would happen if you had another tank below this guy? And this is the reason that we study in 1.5, because that first problem is not linear. It's just straight up separable, and that's easy to solve. You don't need a linear function for that guy. So here, let's have this one cascade into this tank. Nice. So this was our tank 1. And we know that we started off with, was 1,000 liters in it. That's cool. And initially, X of 0 was 100 pounds of salt. Okay. This is going to be tank 2 down here. I'm going to think about this for a second. So this was 5 liters per second. Obviously, if you wanted to have this thing clean out faster, you would increase the flow rate. Yes. So if you were having flow come in and out at 10 liters per second, then obviously that concentration would drop even faster. Okay. Now, here's a question. Suppose I had this dropping into a tank that had initially, let's say this one holds 500 liters, because I can. And initially this one has 20 kilograms of salt. I'll call this Y0 just for a good time. Okay. So think about what's going to happen here. Who is saltier initially? I did that right. Who is saltier initially? This is kilograms. Tank Y or tank X? Who's saltier initially? Am I talking to myself?
Tank 2 is saltier.
Is it?
Oh, I misread that. I thought I said 200. No, tank 1 is saltier. I thought I said 200 over 500.
So we already talked about this. We know what tank 1's going to do. Tank 1's going to tend to 0 over time. That's tank 1. And we knew that before we started this process. Okay. What's tank 2 going to do? Because you said that tank 1 is saltier. So what's going to happen as this one's also draining out at 5 liters per second. What's going to happen to tank 2 initially? It's going to have something.
It's going to get salt, and then it's going to decrease because
Nice. And so yes, as t goes to infinity, the top one's going to become pure water. The bottom one's also going to become pure water eventually. Okay. Now think about that. There's a couple of things here that kind of just make me excited about this. This looks like a what to me? It's like a maximum. Okay. At some point, it will reach maximum salinity. Okay. That's going to be kind of exciting later on. We'll talk more about that, because what happens when you reach a maximum? At a maximum, you will have what? A slope that is equal to
0.
Nice. Initially, we'll have positive slopes, and then we'll have negative slopes again after that. Not bad. Clearly, there's going to be some change in concavity here and here somewhere. All right, there's going to be a concavity change. I don't really care about that. I just like to point that out. That will need to be here or there in this problem. But I know going into this, I know what's going to happen. Right? I know that if I'm putting initially saltier water into another tank, then initially it's going to rise, but then eventually it's going to peter off and go back to 0. That's just it. And so again, that's why I love this class so much, from the standpoint of, all right, this isn't that hard to do. And what I'm doing makes sense. Now I'm going to write this out as if I haven't already done this first part of the problem yet. Was negative, what was it? X over 200, I think. Yeah. Okay. And then I'm going to write dy dt. Well, what's happening to y? Well, I've got this coming into it, right? It's coming out of tank 1, but it's coming into tank 2. Is that right? And then out of it, I'm getting y over 500 liters. Again, this is pounds per liter, and I don't want that. So, and then I'm going to multiply that by, it's going out at 5 liters per second. Again, these guys cancel off. And what are you left with? You're left with 5y over 500. So I'll go ahead and write that out. Because whatever was going out of x is coming into y in this case. And then we got this coming out the other end. Okay. I want you to focus on this piece right here and this piece right here. If you look at them together, what do they form? They form a system of equations. Yes? Okay. Now you think back to algebra 1. When you first started doing systems of equations, they would do something like this. Hey, 3x equals 6, x plus y equals 9. So what did you do? Well, you technically solved the systems equation. You said, well, x is 3, obviously, duh. And then you plug that into here. In other words, you solve this equation all by itself as if it was its own thing. It's exactly what we did up here a few minutes ago, yes? Now we're going to take that result and we're going to place it into the other guy. We're going to put x equals 3 into here and get y equals 6. Okay, that's exactly how we're going to attack this problem. Now, dy dt, and by the way, later on, you had other ways of doing things. You could do elimination, matrices, substitution, good Lord, the matrix equation. You could use Kramer's rule. You could go nuts on, you could graph them for God's sakes. Lots of ways to solve systems of equations. No one ever texts me. This is the second text since I've been talking to you. Ludicrous. Anyway, I apologize. So later on, they're going to get grosser, and you can't solve the one individually anymore. It's not possible to do that anymore. And so obviously at that point, you're going to have another way to go about it. There, I vibrated myself there. Cool. So, but in this case, that's not true. We know what the answer is. So what is our x? Well, we just said our x a few minutes ago. We solved it was 100 e to the minus t over 200. That was our final answer. We're going to replace x with that. This is, in essence, a substitution problem, just like we did over here. We had x equals 3. We plug it back in. Minus y over 100. And yes, I'm going to clean that up a little bit. Nice. Oh, that's beautiful, huh? Huh? What do you notice about this? I'll tell you what I notice about it. This is of the form, this is a linear differential equation. And in a linear differential equation, we're always going to want to get this guy here over here along with the dy dt. So I'm going to add it over here.
Shouldn't it be 0.5 instead if it was x over 200 initially instead of x
Oh, it's
over
x
20?
over 20. I dropped my 0 there. Sorry about that. Yes, 0.5. Beautiful. By the way, we would have figured that out in about 2 minutes when we solved this problem because it wouldn't have matched up with our actual initial values. So that's a good call. Okay. So I'm going to add that plus this equals this, like so. Now, if you recall, if you watched the video from 1.5, I'm going to write it out the way the book writes it. So I'm just going to go to another page and jot this down so you can see what it looks like. This is how they write it out. So you write dy dx. All right, that's simply, this is independent variable, dependent variable. For our case, it's going to be dy dt, the one we're working on currently, plus p of x times y equals some q of x, like so. So the idea here is they want to write this dy dx or dy dt in our case by itself. And so let's go do that. They're going to write it by itself first. So I'm going to write dy dt plus, and then notice that they wanted you to write a function of x times the letter y. Oh, cool. Where is it? Oh, it's 1 over 100. Nice. Times y equals this guy. And I do that just so that you can see it. After you see it about once or twice, you can't not see it anymore. Okay? That means this guy right here is my p of x. And so this is simply an algebraic sleight of hand. Again, if you've not watched the video, go watch it because I go through this pretty in depth. So what you need to do is you need to find our integrating factor, which is what we call p of x. I'm sorry, our integrating factor they call, what do they refer to it? I forget what they call it on this one. They call it, oh, come on. What do they refer to it as? What variable? Oh, the integrating factor. I don't really care what I call it. The integrating factor, we're just going to do this. It's e to the integral of p of x. Okay. So in other words, in this case, it's going to be e to the 1 over 100 dt integrated. Wait, isn't that just e to the t over 100? That's correct. Okay. That guy right here is what we refer to as our integrating factor. Okay, so we're going to multiply the entire equation by it. And just like the cardinal rule of algebra says, whatever thou doest to one side, thou must also doest to the other side. Voila. Here we have e to the t over 100 times dy dt plus 1 over 100. I'm going to write it in this order for the sake of explaining it. And then 0.5, and then I'm not very good at math some days. I'm good at it. Some days I worry about myself. So I'm going to go 1 divided by 100 times e to the, and it should end up being a positive t over 200, I believe, but I'm going to go ahead and do it this way anyways. Negative 1 divided by 200. And it is e to the 1 over 200. Beautiful. So t over 200. Beautiful. Nice. So all that is right there is just an algebraic sleight of hand. But what it allows me to do is this next integral that I'm going to do. Okay. Obviously, this side's pretty easy to do. But this side, this left side, I just made it totally easy. Because again, if you haven't watched the video yet, you recall that back in the day, if you had, I don't know, 3y times e to the y or something, how do you take the derivative of this? You take the derivative of the first times the second plus the first times the derivative of the second. Okay? So if you look at that, that's in essence what we've done. By multiplying by the integrating factor, what we've guaranteed ourselves is that this thing right here, this guy right here is, by definition, this guy when you integrate it. Every single time, don't even think about it. It is the integrating factor times y. Every time. Every time. Okay? Think about that. If this is e to the t over 100, what's the derivative of e to the t over 100? It's this piece right here. Times y. And what's the derivative of y? It's dy dt times the other function. Okay? That is the whole point of that. Again, if you haven't watched that video, go back and watch it because I go through that fairly long process of it. Once you see it, again, you can't unsee it. It's just one of those things. But until you've really latched onto it, it's a little tricky. I'll give you that. Boom. So it's 100. That makes sense to me. Yes, it's 100. Yes, 100. Oh, so 100 e to the t over 200 plus a constant. Okay. Question on that at all? This is the trickiest part, right? It's not the trickiest part. Once you see it, it's the easiest thing on the planet. When I was a kid, they didn't tell us why we were doing that, and it never made sense to me, and I just did it because I was a good little boy doing what I'm told, whatever. Not so much, but kind of. But when I started, I don't know, that when I first started teaching this class years ago, I'm like, that is the maybe coolest thing I've ever seen. I personally am not smart enough to come up with that. So somebody did, and I'm very thankful for that. Now to solve for y, I simply divide by e to the t over 200, or t over 100, you dope. So that give me y equals, now listen, I'm telling you right now, what are you doing? You're taking what you had initially, you're always going to get back to where you came from. You with me on this? Because initially we took e to the negative t over 200 times t to over 100, and we got t over 200. So if I divide that back by what I did previously, I will get back what I started with, which is going to be 100 e to the minus t over 200 plus c. And then, so what is c divided by this? Well, it is c times e to the negative t over 100. And then we're good to go. I wish there was a way I could find this. Well, there is, because y of 0 was, what do you say, 20? Somewhere, 20. Yes, y of 0 is 20. What are you doing? It's 20. And so, well, it would be 20 equals 100 plus c. So c would be negative 80, I believe. And so this right here is the equation that describes what happens with our salt in tank 2. So it is 100 And it is completely a quinky dink that it came up to be 100 again right there. It doesn't always going to be 100. So don't just like, oh, it's always going to be 100 because the other thing was 100. No, in fact, I would argue probably more often than not, it isn't that way. Just is what it is from time to time to time. It's the hardest thing, in other words, to describe to a kid why something works when it's some random quinky dink like 2 times 2 is 4 and 2 plus 2 is 4. Hey, it always works that way. No, it's just some random example you found this one time. So don't bet on that happening every time. There it is. Now let's go see what's looking in with our green function here. Let's go see what's happening with it. Wait, no way. Well, now, no, look at that, will you? What happened again? Now, wait, what happened in negative time land? Nothing happened in negative time land. You with me? It didn't exist. Time starts at 0. Okay. This must be the land in which my bosses always live at the high school because they think time started when they showed up. But anyways, in this situation, that's truly what happened. At time equals 0, we took measurements, we hit go, boom, things happened. And again, somewhere in here, we had a maximum. So at 94 seconds, we had a maximum salinity of what? Well, of 31¼ kilograms of salt. Okay. And then again, both of them will peter off to 0 at some point. Okay. Yeah. I do want to do one thing just for fun. This is just, I'm just going to take this a step farther just for fun, to kind of just relate it to something that we already know. 100 e to the negative x divided by, that's not to the 100, you dope, divided by 200, minus 80 e to the negative x divided by 100, comma x, boom. So there's my derivative, yes? So if I take that derivative and I solve it, equal to 0, 4x, it should be 94. Well, it would be 94 if it rounded it off for us. Yes, it's like I know what I'm talking about. How freaking cool is that, huh? And again, it started at 20, so I feel fairly confident in myself. Yay! And it follows the pattern that I thought it would do, which is it tails off towards 0. And at some point over there, it's going to be in essence 0 because it will have run out of steam. So all tank value problems look like this. Could you have a 3 or 4 or 12 cascading? Of course you could, but that's the game. Questions on that at all? Does that help or hurt? David, you asked the original question. Was it Lucas? Who asked the original question?
Yeah, that was me. I think it helped. No, that was really helpful.
So again, go back and look at it, the videos. But the thing I love, again, the thing I love about this class, this particular material is that it makes sense, right? If you're putting saltier water into a less salty tank, the second tank is going to increase in salinity for a while. Then you know it's going to go to 0. That's beautiful. You can always go back and check yourself when you're finished and see how well did that pan out. Okay. Any other questions you want to see? Okay. Well, speak up later, I guess. If I'm going to do a couple of examples here today and just talk about a few things. So when you guys did slope fields the other day, some things that I don't think we talked enough. Well, it doesn't get taught. If it was me, slope fields and like section 2.3 or 4, 2.3. I think it's 2.2. Maybe it's 2.2. One of them. They would be done at the same section if it was me, because to me it just makes sense. Okay. So when you graphed some slope fields the other day, let's see. Do I want to just make one? I'm just going to do one like this. Let's do this. Slope field generator. Bam. And this Bluffton one is probably my fave, I guess. I don't want to do that one. That's boring. Let's use, where's your, there we go. Here, you go away, you quit, you do this. Let's do this. 0.1 x times parentheses 20 minus x or something of this nature. And our window sucks. course it does. Oh, I can't do X though. Sorry, I do Y. I forgot this goofy thing is X versus Y. I was thinking Y versus T. My apologies. We'll get there. -3 is fine. Let's go up to like 23 or something just for fun. Boom. And what you'll notice is that it seems to be fairly horizontal line-ish at right around 20, yes? That is, above 20, it was negative, and below 20, it's positive slopes, yes? So that suggests that right around 20, we're going to have basically where zero slope would happen. In other words, if your y, which is your independent variable, gets up right around 20, nothing's going to happen, okay? Now, if I were to do this, click on here, you can see what happens. It starts somewhere, again, this is, right here I let x go negative, but if I didn't let x go negative, it would start right here at x equals like 5 or y equals 5-ish or something. And it would go up there and it would tend to peter off toward this value, okay? Same thing down here. If you started above it, you'd see it would come down and it would taper down toward that line. And then down here, you'd see it would go away from that line, okay? And so what we're going to be looking at today is a couple of different things. We're going to be looking at an application, number one, but then also going to be, while we're doing that, I think thinking through a different way of looking at it. So if I said to you, hey, dx dt, or yeah, dy dt, I guess. Well, yeah, I'll do dy dt, I guess. It doesn't make any difference. And then I put 0.1 x and then 20 minus x. Okay. This equation talks about the slopes, or rate of change, if you will. And again, you'll notice it's all in terms of my, x value, which is my dependent variable this time, okay? Because t is my independent variable. There will be times when, obviously, I'm always going to be interested when the rate is 0. Because when the rate is 0, what's happening? Nothing's happening. Well, what would that mean to me? It would mean to me, if it was the case of a population, we would have reached what we call equilibrium. Okay, so we talked about maxes and mins in Calc 1. We talked about, listen, you come to this spot, you reached a maximum, and you throw a ball up in the air, does it stay there? Not unless you're Bugs Bunny or something, no. It goes up, it comes right back down. Is it in equilibrium at the top? No, it's at a maximum, but it's not technically in equilibrium. At gravity, for instance, is still acting on it the entire time it's flying in the air, okay? In this situation, what we're saying is that when x equals a certain value, we are going to reach an equilibrium, okay? And what would happen if we got there? Well, nothing would happen. So there would be no change. That's correct. So if we're at this value, there's no change. What would there be tomorrow? It'd be the exact same, because there's no change. Okay, and that's the slight difference based on whether we're at a maximum or a minimum versus this, which says if you reach a certain value, there's no change. And if there's no change at that value, what will it be from now on? It'll be that value from now on. Okay, so in this case here, if you think about it, let's set it equal to 0. And you're like, hey, this looks like a quadratic. It is a quadratic. You're right. Good job. And so that's number one. There should be 2 answers to it, and there is. X equals 0 and x equals 20. When x equals 0, we're going to have equilibrium. And when x equals 20, we're also going to have equilibrium. Okay, because those are the 2 values in this case that give us a 0 slope or 0 rate of change. Oh, that's nice. What would that look like? Well, the way I like to envision it is, here's 0, and here's 20. Well, what could you be? You could be below 0, you could be between 0 and 20, or you could be greater than 20. Let's start off with greater than 20 just for fun, shall we? If you put a number in bigger than 20, and I don't care which one it is, this will be positive. This will be negative. Negative times a positive is a negative. So we will have negative slopes up here, negative slopes. And again, I don't care what number it is, 20.2, or it could be 1,000,000. Doesn't make any difference. It'll end up with a negative up there. Okay? What happens in between here? Let's say you put in x equals 18 just for fun. But it doesn't matter, any value in here. Positive, positive, positive times a positive is a positive. We have positive slopes in here. Positive slopes. And then what happens if you put a number in that's less than 0? Well, then this one becomes negative, and this one's still positive. Negative times a positive is negative. So we have negative slopes down here. That is as hard as it gets when it comes to categorizing. And so we have a name for this. This guy here, where they're negatives, they're approaching from the top like so. And they're positive, they're approaching from the bottom like this. We call this a stable equilibrium. If you are laying flat on your back on the floor, you really can't move anywhere, okay? By gravity, you're not moving anywhere. You are as stable can get, okay? If you're balancing on your tiptoe on the end of a baseball bat on top of a beach ball, that is very unstable equilibrium, sir. You are likely to come crashing down in a few minutes. And that is what we call this one down here, where on the one side you're going away from it and the other side you're going away from. We call this one down here unstable equilibrium. Because on both sides of it, it goes away, okay? Different books refer to it differently. When they, some books call this, I figure they call this one a funnel, and they call this one a trumpet or something. That just confuses me. Time runs this direction. So as you're coming this direction, everything is coming together. That's stable. As time goes, again, this direction, everything's going apart. Unstable equilibrium. And if you ever run into one that looks like this, well, it's like it's unstable and stable at the same time. That's right. We call this guy semi-stable equilibrium, okay? And it's exactly what you want. You're like, well, could it be the other way? Of course it could. You could be coming down on the one side and going away on the other side. Again, that is semi-stable, okay? If you think about it, there's negative slopes, positive slopes, negative slopes, positive slopes. In this case, they are both positive slopes or both negative slopes. So that's how you can tell them apart. Okay, it's not very difficult. You'll see a few of these. Dx dt equals x 20 plus x minus 3, whatever. Clearly, your solutions are going to be 0, negative 20, and positive 3. So negative 20, negative 20. Again, what happens at negative 20? If you put in negative 20 fish into this pond, which I don't know what that means, it would stay at negative 20 fish. It would never change. Or 3 fish, I guess, if that makes you happier, right? If you exactly 3 fish, what's going to happen? Nothing's going to stay put. Okay. And then, of course, you could do 0 as well. Any of those, you're not going to have anything change. So when I look at this problem down here, I could be down here at negative 50 or something. I'll put in a number so it makes me happy. This is negative. This is negative. This is also negative, I believe, yes? So negative times a negative times a negative. These are going to be negative slopes, like that. If you put in a value, say like negative 10, again, just so it's easier to get a visual on it, negative, positive, negative. These will be positive slopes, so something like this and something like this up here. We know that they're, in essence, they are, what they're going to form is horizontal asymptotes. You want to think of it like that, okay? So that's why it's not going across like this. It's coming up and approaching it. And as soon as I do a couple of example problems here in a few minutes where we actually apply this is a little algebra. It isn't that cute. But when you start looking at it in terms of population growth, it makes so much more sense, okay? And then if you do a number like, I don't know, 2 or something, we got positive, we got positive, we got negative. That'll be negative slopes in here. And then like 4 or something, they're all positive, so positive slopes. So that means this guy is unstable, stable, unstable again. Okay, and it literally, that's what section 2.2, 2.3, one of those. That's what it's all about, and you're going to be looking at it from that standpoint. Not a very hard concept, a little bit of algebra, a little bit of thinking. In my mind, that's easier. You could, instead of drawing it the way I did it, you could graph them all in here, and then you could see them, and like, oh yeah, sure enough, that guy right there is stable. This guy down here is unstable. If that makes you happier, I personally, I could do this all day long. Isn't that pretty? But to me, it's easier for me just to draw it out like I did down here. Like, to me, it just helps me, I don't know, see it better. Okay. Now, the reason I mentioned that first, because again, if I was writing the book on this, I would put those sections ahead of section 2.1. But in section 2.1, it's all about population models. And there's a video about it, but I want to talk about one part of it today, just a little bit, and then show you how to use your calculator a little bit better too, as far as helping with the intervals, okay? So what you're going to see is one that looks a lot like this. And one did I want to do? I had one earlier in my head. Oh, fiddle. Oh, yeah, let's do that. Yeah. Okay. You'll see it written this way. You'll oftentimes see it written this way. Okay. In either case, this is what we refer to as logistic growth. And I'll show you why it's called logistic growth momentarily. Okay, well, we need to solve this guy. Okay, so I'm going to work through it by hand first, and then I'll go back and show you how you could help yourself out with using a calculator. The calculator, the reason I like to show it both ways, calculator, you think it's easier, it kind of is, if you understand what it's telling you. But it won't look exactly the same as when you do it by hand, so it kind of freaks a person out. So just be aware of that. Okay, this is a separable differential equation. So let me separate it. Cool. Here, I'll do the hard part. Oh, crap. I got to integrate this mess. Yep, you sure do. So how do you integrate that one? There's always some kid in every class that remembers how to integrate this. How do you integrate this guy? Anyone? Emilio, I think I taught you Calc 2. You should know how to do this. Not to call you out or anything. Anybody remember that one?
Power.
Oh, use substitution? Alexander? No. What about you, Isaac? You said?
I was saying, so you put it to, you do x times 10 to the negative x to the negative 1, and then you can distribute that, and then you can take the integral.
No.
Partial fractions.
Yes! God help us, we love partial fractions. I don't know if we love partial fractions. I'm not going to lie to you. But they are fun every now and again. Okay? Partial fractions. Nice. And so if you've forgotten, it looks something like this. Right? You separate them into the two fractional component pieces. And then we're going to multiply by the common denominator to clear fractions. So you get 1 equals a times 10 minus x plus bx equal 1. I'm going to go ahead and show you the way that I learned it, and then I'll show you another cute trick someone showed me some years ago, and I was like, oh, that's neat. I wonder why I never learned that. I just distribute personally, so that's 10a minus ax plus bx. That's cute. So what do I know here? These are my constants. These are my constants. So 1 better equal 10a, which means a is 1/10. And b minus a, those are my x's, better equal 0. Why? Because there's no x's over here. So b better equal a. Okay? And so then if b is that, then I guess then b is equal to 1/10 as well. That's how I was taught to do it. That's the way it usually makes the most sense to me. The other way to do it is to come up here and look at this. What value of x would make that 0? Well, 10. So if I put 10 into here, this piece cancels off. If I put 10 into here, I get 10b equals 1, which means b is 10. That's one way. And then what is the other 0 of this function? Which, oh, fart. Oh, no. Hope it saved it. We're sorry, we crashed. Oh, great. Awesome. Yay. Press enter. Click here. Oh, yes, reload the page. Okay, whew. Nice. Okay, so the other 0, or by the way, equilibrium solution was 0. If you plug 0 into here, this piece cancels off. 10 minus 0 is just 10. And so then you get 10a equals 1, and a is also 1/10. But whatever makes you happy makes me happy. Now, what do we do then? Well, if we're going to integrate this fella, we're going to rewrite this side as the integral of 1/10 times 1 over x dx plus 1/10, oops, 1/10 times the integral of 1 over 10 minus x dx. Okay. And so this is 1/10 ln of x. Now, someone said U substitution earlier. This is where the U substitution happens. No, negative dx, stupid. There you go. So this ends up being negative 1/10 ln of 10 minus x. Okay, equals t plus a constant. These guys have a 1/10 in common, so you could pull it out front. I'll go ahead and run through this step slowly. I think I'm gonna leave the 1/10 where it is for right now. I know I could times it the other side, but I'll just leave it there for right this second. When you subtract logarithms, remember that's the same as dividing. So it's gonna be x divided by 10 minus x. And now we're home free. All we have to do now is solve for x. So to do that, I'm gonna times both sides by 10. So 10 times t is obviously 10t. 10 times a constant is a constant. Now, I know I've done that in videos. I will continue to do that. That is a big deal. A constant times a constant plus a constant minus a constant is another constant. And I don't care what that constant really is until the very end product, okay? So 10 times a constant is another constant, okay? Now, I'm going to exponentiate both sides. So I'm going to get x over 10 minus x equals c e to the 10t. That's exactly like we did when we did a separable differential equation earlier, like that first tank we did. And then now we get to play a little bit of gamesmanship here. So c e to the 10t times 10 minus x. We'll distribute. Ten c e to the 10t minus c e to the 10t times x. Some people right now would say, what about that c right there? 10 times c is technically technically another c. I would agree with you. However, for the purposes of what I'm doing, I wouldn't probably do that this time, but you wouldn't hurt you if you did either necessarily. The reason I don't want that is because now there's a c here and a c here. Okay, those are the same c's. But if you took 10 times this c and you called it the same, it's not the same c anymore. You with me? So I don't want that to happen this time. Now I need to get this x over here. So let's add them. Nice. Hey, what do these guys have in common? They've got an x in common. Hey, let's divide by that. Nice. So technically you solve this problem. Most people, however, will do this top and bottom. Oops. Most people will, at this point, will do the following, and there's a real good reason for it. And so you'll get x equals 10 over, so I'm going to get 1 over c e to the 10t, I want to write it like that, plus 1. And then most people will finish that off by saying x is equal to 10 over, they're going to call this c e to the negative 10t plus 1. Oh, that's awesome. And the reason they do that is this. What happens to the denominator as t goes to infinity? The denominator becomes 1, which means x approaches 10. And that's a big deal, okay? And the reason we make a big deal about that is because let's go look at our solution. Our dx dt was x 10 minus x, I guess. Our equilibrium solutions were x equals 0 and x equals 10. Interesting. Wow, interesting. So if I look at this problem here, at 0, if you put in a number and then 10 up here, 10, 0. I'm not really interested in negatives. I could find them if I wanted to, but if this is actually describing, let's say, a fish population, I'm not going to look at negatives. I don't care. So if I put in a number like 5 or something, 5 times 5 is what's positive slopes. I'm going to have positive slopes in here. And what happens if I do, what happens if I put in a number bigger than 10? Let's say I put in 12, well, it says 10,000 fish. If I put in like 12,000 fish, what's going to happen? Well, they're going to die off. And so if you think about that, it makes sense. This is positive times a negative. They're going to have negative slopes up here. But in either case, what's going to happen? It's going to tend to that amount. And so we call this amount the carrying capacity. This is how you decide if you, well, in theory, this is how you decide how many fish you're going to allow to be caught this year. This is how you decide how many, in theory, how many deer you're going to let be shot this year, whatever it is, because you know there's only a certain amount of deer that this particular unit, management unit can sustain, or this is how many fish this lake can sustain. So if it ever grew in population bigger than that, they're just going to die off anyway. So you might as well people fish them out, makes it for a healthier population or similar. Okay, that's the idea of this. And so the reason that we write it in this format is so that we can see what's going on. Okay. Did I give an initial condition for this one? I did, didn't I? I said my initial condition was actually equals 1, I believe. Is that right? Is that what I said? Yes. So x of 0 was 1. And so just like every other function we've done, look what's going to happen. Well, you can put 1 into here. You're going to get 10 over c plus 1. And you can solve this, but might I suggest that it's easier to solve for c right here. Okay. So if you think about that, let's plug it in there. You're going to get 1 equals c times e to the 0 is 1. And then you're going to get 10 minus 1. So you get 1 equals 9. What just happened? 1 equals, oh, no. Yeah, no. Yeah. What happened? 1 equals 9c. Oh, right, yeah. But be careful when you do that. Be careful when you do that. That's right. But be careful. Down here, what did we do? Right here, we had 1 over c, and we changed that to c. If you solve this equation down here, right here, you will get the c plus 1 is equal to 10. If you multiply this to both sides, and you'll get c is equal to 9. Be careful where you solve it. You can solve it wherever you like, but just pay attention to what you did. Like you did it, you got that it should be 1. You said it should be 1/9 when you solved it earlier up the page. You checked the back of the book. Or more perfectly, you, instead of checking the back of the book, more perfectly, you just graph it and go, does that make sense? And with 1/9, no, it doesn't make sense at all. And what I mean by that is if you come back into Desmos, it was 10 divided by, what was it? 9 e to the, can't remember what the problem was, e to the negative 10t negative 10x plus 1. Nice. And notice you have to zoom in quite abruptly on this one. Why? Because it grows like a bat out of heck, yes? Because this growth rate is huge, okay? But anyway, that picture right there, what you see right there is what we call logistic growth. This is how you grow, okay? When grandma says you grow like a weed, she's talking about in this neighborhood, yes? And most of us didn't grow quite this fast. Some of us would have done it a little differently. Now, obviously, it's a different problem, so watch me change this here just for fun. But let's say you make that 0.5 or something. Look what happens. Well, you just slowed the growth rate down, okay? So in the problem I gave you initially with the 1 there, or with the 10 there, then obviously it was a huge rate of increase. And then, of course, in this particular problem, and again, this is a completely different problem, but what would happen is that it's still exponential. It's still doing its thing. It still is what we call a logistic growth rate, but it's so slow that it almost looks linear over a certain period of time. Speaking of that, the other day I was reading an article by someone who really wanted to make the COVID thing look worse than it is, or whatever. They tried to make it look even worse than it is. And they were talking about in what people refer to as exponential growth. I got news for you, friend. Every population has an exponential growth component to it. every one of them, okay? Even if it's almost perfectly linear, that is, over a very short window. Like over the last 10 years, it's been like 500 people a year been moving to our town. Well, that sounds linear. Yeah, it does sound linear. It almost looks linear, but why? If you have a very teensy tiny percentage of growth, teeny tiny percentage of growth, then 500, like be 500 be the percentage of it is 1 year, like 502 people the next year, but it's basically 500 is the same basic percentage. Why? Because it's such a tiny little percentage of growth, okay? And so you just gotta be well aware of that. In this situation here, you have both the concept of an exponential growth and almost a decay in that it's growing, but it's petering off, okay? This is what logistic growth always looks like. It's how every organism grows. It's how every population, for the most part, grows, okay? And it's always that way. When you talk about infecting people, that at some point in a closed population, at some point, everyone will have the problem, okay? At which point you will have reached maximum and then no more is getting, you know, they're not getting infected at the same rate. Right in through here, this is where your maximum rate of infection is occurring. How do I know? Because that's the steepest rate of increase is right in this neighborhood. And then it starts tapering off. Years ago, I don't know, probably it's about 10 years ago now. Guy I worked with, his son was in my calculus class. And I said, you know, it'd be cool. I've always wanted to do it. Let's start a rumor and let's see how fast it spreads. And so he had gotten busted for a MIP that summer. And so we started a rumor. He actually started, one of the buddies in his class started the rumor at 8:30 in the morning or 9 o'clock in the morning. And at 2 in the afternoon, I went on the intercom and I said, raise your hand. And if you've heard a story about this kid Casey today, and we had all the teachers count up how it does. And we measured it, and it was pretty amazing how fast the rumor spread. However, there's like 800 kids in the school at the time. And so at some point, most people have heard it. So like you walk around school, hey, have you heard about Casey? Yeah, I heard about it. It's harder to find someone who hadn't heard about it, okay? Initially, it's like, have you heard about Casey? What about him? Tell me about him. And initially, it grew really fast. One thing I didn't take into account, though, small town. And so it got back to his mom. She was not pleased. And then I had to like call and apologize and whatnot. His dad thought it was hilarious. But the mom was not happy that her kid had got another MIP, which I don't really blame her, but it was kind of funny. So you're going to be doing that a lot. I would just say this. I want to run through this integral one more time, but using my calculator to help me out. And it goes a lot faster with just the calculator, but it looks a little bit different. And by the way, this is super fast growth. It's going to be all about this number right here. If this number is very small, like 0.01 or 0.1 or 0.5 or something very small like that, then my growth is going to be a lot less fast. Okay, but right now it's 1. That's a huge amount of growth. So I'm going to do the same thing I did last time. Come to here. And then what I'm going to do is, the only part I'm going to do differently is, you know, do the calculator portion to integrate this guy. Okay. So, but I want you to see how different it kind of looks when you do this. So integrate 1 divided by x times. Don't forget to put the times there. Betsy does not like that because they don't understand implied multiplication. So you see, you get this mess right there. You're like, wait, that looks different than what I got. It does and it doesn't. Understand that it pulls a negative out of that. Okay, and so it looks different, but it's not really that much different from us here. So what you can do to do this problem is go solve this guy. Now, I say you can do it. Let me just show you what it looks like when we do it here. I don't know if I cleared my C. I normally would just use C here, but I'm not sure if I've cleared C, and I don't want to go take the time to do that right now. Yeah. Okay, that's not wrong, but do you see how disgusting that looks? Okay, that is not wrong, but it is disgusting looking. But notice you've got that one, and you've got this one over here. Okay, but this is important. So this is important to keep an eye on this guy right here, and then see what happens to it. Okay, the -1 there is a little screwy. Oh, I know what happened. So the -1 bit right there is one of the things that you run into. You're like, oh, this is going to help me out. Not so much, I don't think. But let's write this down, and we'll take a look at it. So you've got 10 e to the, what did I say, 10t plus 10 cubed over e to the same thing minus 1. Oops, 10 cubed, sorry, my bad. Now, I will say this, just be careful when you're doing a problem like this. This right here, you've got e to this power right there. E to this constant power is what? Well, it's a constant. So you end up with this thing right here. This is the same thing down here. And then minus 1. The only problem I have with this is that negative sign sometimes pops out. And the reason that that negative sign pops out is because they do not include the absolute values on the other side, okay? And that's just something to be careful of. The calculators are wonderful things, but they don't always give you the right true answer, because right here where it says the ln of x minus 10, in theory, those should be absolute value signs, okay? So I guess my point by saying that to you is just be careful. Be careful when you're using the calculator to do integrals. I have no problem with you doing them, but if I had never done all these problems and I had seen that and I hadn't caught myself with that -1, and I'd be out of luck and I wouldn't know where the answer is supposed to be. If this had ever been a negative right here, look what that means. I'm just going to write a big constant. I'm just going to write a constant. So you got whatever on top. Let's just say it's 10, and then you've got c e to the 10t on the bottom or whatever, minus 1. What would happen if there was a negative here? If there's a negative here, that means the denominator could equal 0. If the denominator could equal 0, what's going to happen to my population? Graphically, what would happen to it? Oops, let me graph this real quick. If here's your x and versus t, what happens as the denominator goes to 0? What's going to happen to my population? What's the graph going to look like? We're still late. Anyone? Anyone?
It'll go to infinity.
So live.
Yes. Would that be an issue for you? I'm thinking that would be an issue for me. Okay. And so it turns out that there's actually a population model that's called, wait for it, the extinction explosion model. And it matters what your initial population is. If you're above a certain amount, it's going to blow up to infinity. They call that doomsday, by the way. Or it's going to crash to 0. And so it would be a very unstable population. I think the classic is always rabbits, how fast those suckers reproduce. And in theory, they'll just keep breeding, to infinity. Obviously, that is a simplified version of it. But again, why would it go to infinity? Because you could end up with 0. This is always positive. If this is positive, the denominator will never be 0. In fact, this would tend to 1 over time. And so it would never have this asymptote look to it, okay? So by all means, use the calculator to help you. I would just argue that this mess right here is not helping you at all, and to be cautious about it when you do it so that you don't confuse yourself. Anybody else think of any questions you had? You want to see while I'm here? Oh, good Lord, I'm staring at myself. No? No? Everyone's quiet today. Well, all right, man. Oh, Lucas got a question. I didn't mean to cut you off. Go.
Yeah, hold on one second. I need to find exactly what section it was in.
Cool.
Okay, so 2.4, number 1.
Nice. Getting there, hang on. 2.4, number 1. By the way, the reason I like to do 2.4 with the chapter 1 stuff, I think it's easier to kind of start from that situation. But just be careful with it. So 2.4, number 1. So
Yeah.
y prime is -1. There's negative y rather. Y of 0 is 2. And then y of x is equal to 2e to the minus x. Okay? So we're going to apply Euler's method twice to approximate this solution, the 0, 0 to a half. Okay, cool. So the first step size being 0.25, then with step size being 0.1. Compare 3 decimal places and then to the actual solution. All right, cool. Okay, so basically what they want to do is they want to know, hey, what is y of 0.5? Okay, using Euler's. And then stick in y of 0.5 into the actual and see how close you are. And they just want you to get a feel of, well, what does that look like for us? So I'll go ahead and bust it out on the big computer here. And so you can see me do it in Excel real quick. And maybe, is that working? Yep. And Excel, there we go. So y of 0 was 2. By the way, you can see why if y was 0, we'd have a problem, right? If y was 0 initially, we'd be screwed because it would never grow. This is exponential growth. We are going to be taking a percentage of what we had previously. Well, any percentage of 0 is 0, so we would add 0, and that's no bueno. So in a situation like this, obviously we're going to have to start with some amount of something, otherwise you're going to be hurting for certain. So here's y, okay? And then over here somewhere, I'm going to go ahead and put y prime. And then I'm going to put in my step size over here somewhere. It doesn't really matter where you put your step, okay? And we'll start with 0.25 because that's what they asked us for. And I'm going to go ahead and show you how I'm going to do it every time. So you get comfortable doing that. Because eventually I'm going to not do just 2 step sizes. Obviously with 2 step sizes, I do that with a calculator. Or on a piece of paper. That's not what I want to do this time. So I'm going to go 0. That was where we started from. And we're going to say equals this guy plus. And we're going to click on this one here. And then make sure you get F4. Where's my function? F4 button. There you go. And what does that do? Well, it takes and it's going to make sure it's locked into cell E2, what those dollar signs do. F4 always does that. If you ever have an issue, like my stupid tablet doodad over here, sometimes when you get the function F4 doesn't work, you can just put in $E, $2. It works that way too. And then we'll drag it down. Now, again, you could just put plus 0.25, you can, but I like to be able to then change my step size quickly. And I think to me, that makes a lot of sense to start there. We're going to start at 2. So this is equals, okay, what is our derivative is negative whatever y was, right? So that's what our slope is going to be initially. So this is equals, so it's, remember the function, Euler's method is really just slope-intercept form. It's y equals mx plus b. So I start off with the b part. I'm going to start with where I was previously. And then I'm going to add that, I'm going to add my slope to that times my step size. Okay, so it's y, so right now it's y equals b plus mx. That's how it's always going to be. And then make sure, keep your dollar signs on there, because when I drag it down in a minute, I want it to stay on E2. So go ahead and drag this dude down. Oops. And then grab them both and drag them down. Okay, so this is what I'm saying. I am saying that y of 0.5 is approximately 1.125. Let's see how close we are. So the original equation that they said it was is supposed to be 2e to the minus x. So 2 times exp of negative 0.2, or I'm sorry, not negative, dummy. Yeah, negative 0.5, because that's one. Yeah, negative 0.5, because I'm interested when x is 0.5. Negative, so this is the actual value. This is my approximated value. Geez, I'm off by, I don't know, let's find out. Just see how close I am. I'm off by about 7% from actual. Not terrible. Could do better though. So a better way to do this would be to go 0.1. Okay, I'm gonna get rid of this because it doesn't mean anything anymore. Because right now, look where we're at here. Okay, well, right now, I'm gonna drag all these guys down. I want to drag it down until I get to 0.5, which should be here-ish, right? Boom. And now I'm at 1.18. You're like, oh, it's better, but it's not a ton better. You're right, it's not a ton better. So then I could go, well, let's go by 0.01. And the reason it's not a ton better is because we're using a linear approximation, okay, for an exponential growth. Oh, good Lord, where are you going, stupid? Sorry, I got a little carried away with myself there. Got excited. Oh, look at that, friends. 1.21. 1.21. We're off by 0.003. Yeah, it's good enough for government work. If it wasn't good enough for government work, well, then by all means, go out to 10,000 decimal places or whatever you need to go to, and you can get as close as you want to get. But again, herein lies the rub. When you're using Euler to approximate what are almost exclusively going to be some exponential kind of functions, is that you're going to be, it's not the best, but it gets you thinking. So then later on, we'll get into the Runge-Kutta method and some of the other methods, which are better versions of this. The principles are the same, but you just have a little better way of going about it. Okay, thanks. That help you out there?
Yeah, so should we be doing these in Excel, and then do you want this attached to the homework, or should we just list out our answers?
You can just list out your answers. That's fine. On the test, you're going to turn in your spreadsheets with the test.
Okay.
Yeah. I just want you to feel comfortable with Excel because that's what you're going to be doing. I mean, this problem, that's why I don't like the way books usually do things. Do it for two things. Well, you're like, why am I going to break out Excel for that? Well, I think you should be doing it for, it's approximate for x of 10. You look at x of 10, good Lord, you're off by 8 million or something. You're like, that's ridiculous when you're, counting by like ones or something. And so then you can really see how close you can really narrow in on the thing by using a tinier step size. So, and then I think it's nice on this one because they gave you what the answer's supposed to be. But in reality, understand that the reason we're doing a lot of numerical solutions is because there isn't a solid I can get y equals every time. So this one's nice because we know what the answer is supposed to be. Or we could do the same thing with this population growth we did with the logistic growth when we did a few minutes ago with the 10 problem. We could have done that one as well. We could have used that to approximate it over time. Because I know what the actual answer is, I could tell you how close I am. But when I run into one that I can't do, that's where numeric solutions come into play. And so that's what I really want you to understand, how numeric solutions work. Okay. Anybody else?
Yeah, I just had a quick question about, because you said like we would have to, for like the exam, turn in the spreadsheet. If we were to do that in, let's say, MATLAB, would we just turn in like a screenshot of our code and the numbers, or?
Yeah, that'd work.
Okay, cool. Because as you're going through that, I was like, I was seeing how I would do it in MATLAB since I'm more comfortable with that. And yeah. Okay. Thank you.
Yeah, I'm not married to Excel. I love it. I'm not married to her anymore. No, but yeah, Google Sheets, whatever, MATLAB, whatever you're happier with. And certainly they can be done in all of them. I could even I could even get it to do that in I know I've done it before in a TI-89. It's a gross, weird way of doing things, but yeah, whatever you're more comfortable with is fine.
Cool. Thanks, Jay.
Yep. All righty, everybody. Have a great day then. See you on Friday for office hours, I reckon.
Yep. See you then.
Awesome.
Bye.
Thanks.
Thanks.